In this video, I'm going to be doing an example of using a Taylor polynomial and Taylor series to approximate a function. So there's 5 things that we want to be able to do as identified here. And so in this particular video, I'm going to use the example of a function f of x is equal to e to the 3x plus 1. And we want that to be centered at x equals 1. So in other words, our c value is 1. So the first thing we need to do is to write the Taylor polynomial. And this will be a Taylor polynomial, not a Maclaurin polynomial. Remember, a Maclaurin polynomial is a special type of Taylor polynomial centered at 0. Since this is centered at 1, we can just call it a Taylor polynomial. And so the general formula for a Taylor polynomial, and let's do this out to P3. So the general formula going out to P3 is going to be f of a plus f prime of a times x minus c plus f double prime of a times x minus c squared over 2 factorial plus f triple prime of a x minus c cubed over 3 factorial. And again, the easiest way to remember this is everything is, we have all the 3's together. Third derivative, x minus c to the third over 3 factorial. Second derivative, x minus c squared over 2 factorial. And the first derivative, x minus c, is really raised to the first power divided by 1 factorial, which is just 1. So to do this, we need to start by finding the various derivatives. So let's just start with f of a. f of x is equal to e to the 3x plus 1. So let's evaluate that at 1. So evaluating that at 1, we have e to the 3 times 1 is 3 plus 1 is 4. And we'll just leave this in terms of e. Then the first derivative of this function will be 3e to the 3x plus 1. And evaluating the first derivative at 1, we get 3e to the 4th. Then we want the second derivative. Well, the second derivative is going to be 9e to the 3x plus 2. And again, I'm just using the chain rule here. And the second derivative evaluated at 1 will be 9e to the 4th. And then the third derivative of x will be 27e to the 3x plus 1. And the third derivative evaluated at 1 will be 27e to the 4th. Now, when we're doing the error calculation, we're going to want to find the fourth derivative. So I'm going to do that in blue here. The fourth derivative of x is going to be 81e to the 3x plus 1. Okay? And evaluating the fourth derivative at 1, we will have 81e to the 4th. So we're going to come back and use that a little bit later. But for our Taylor polynomial, all we need are these. And so f of a we have right here. And then f prime of a we have right here. And f double prime of a is right here. And f triple prime of a is right here. So those are part of the coefficients of our polynomial. The other part of the coefficient would be the factorial in the denominator. So let's put that all together and create our polynomial. The polynomial p sub 3 of x is going to look like e to the 4th plus 3e to the 4th times x minus 1 plus 9e to the 4th x minus 1 squared over 2 factorial, and then we'll have 27 e to the 4th x minus 1 cubed all over 3 factorial. That will be my polynomial. So that's the first objective, is to create a Taylor polynomial that represents this particular function. Second thing then is to create the Taylor series. And so to create the Taylor series, we'll start at n equals 0 to infinity. Sometimes it's kind of difficult to just go by the very first term. So start looking at the subsequent terms. This is n equals 0. This is n equals 1. This is n equals 2. And of course, this is n equals 3. So it looks like, first of all, we have a 3 to the first power, 3 to the second power, 3 to the third power. So we're going to have a 3 to the nth power. Well, each one of these also has an e to the 4th, e to the 4th, e to the 4th, e to the 4th, e to the 4th. So my series will have an e to the 4th in it. And remember, e to the 4th is just a constant, it's just a number. Then we have x minus 1 to the nth power. And then that is all being divided by n factorial. And so there is my Taylor series representation. This is the Taylor series for f of x equals e to the 3x plus 1. All right, the next thing that we want to do is always to determine what the interval of convergence is. So the interval of convergence, interval, and of course the radius of convergence, we use the ratio test. So we're going to use the ratio test. And so to use the ratio test, we want to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So a sub n plus 1 would be 3 to the n plus 1 e to the 4th x minus 1 to the n plus 1 over n plus 1 factorial. And then instead of dividing by a sub 1, we will, as always, multiply by its reciprocal, which will be n factorial over 3 to the n e to the 4th and x minus 1 to the n. The next step is to simplify it. So some of these terms can be simplified. 3 to the n plus 1 can be rewritten as 3 to the n times 3, and then times the e to the 4th. X minus 1 to the n plus 1 can be written as x minus 1 to the n times x minus 1, and then the n factorial from the second fraction, put it all over one big fraction now. And then n plus 1 factorial, I'm going to break that down into n plus 1 times n factorial. And then in the second fraction, we have 3 to the n, e to the 4th, and x minus 1 to the n. And so a lot of stuff's going to cancel out. 3 to the n cancels with 3 to the n. E to the 4th cancels with e to the 4th. X minus 1 to the n, those cancel out. The n factorials cancel out. So what I'm left with is a 3 x minus 1 over n plus 1. So I now have the limit as n approaches infinity of 3 x minus 1 over n plus 1, and then that becomes x minus 1 times the limit of 3 over n plus 1, because we can remove the term that has the x in it because it has no influence on the limit. And so this then gives us absolute value of x minus 1, and the limit is 0. Well, the absolute value of x minus 1 times 0 is 0. And is 0 less than 1? Remember, our test convergence says that our limit has to be less than 1 to converge. Well, 0 is always less than 1. So this will always converge. It always converges. What do I mean by always converge? For any x. For any x values. And so therefore our radius of convergence, if you will, is infinity. The interval of convergence is from negative infinity to positive infinity. That means if we take this polynomial out infinitely far to an infinite number of terms, it will converge with the actual function everywhere, not just over a given interval. The next thing we want to do is approximate the function. This is step number 4. We want to approximate our function. And let's use approximate f of 1.1 using p3 of x. In other words, using our polynomial. So first of all, let's just find out what f of 1.1 is. F of 1.1 is going to be e to the 3 times 1.1 plus 1. And we'll do this in Desmos. Use Desmos to do this. And then we want to find p sub 3 of 1.1. And so we will also do this in Desmos. So let's wander on over to Desmos. All right, so here we have, up at the top, the function evaluated at 1.1, and we get 73.6997. So let's write that down, 73.6997. So f of 1.1 was 73.70. Such a short to remember. 73.6997. 73.6997. And p sub 3 at 1.1. So going back to Desmos, here is p sub 3. I just entered it into Desmos as a function. And then I evaluated that function. P sub 3 1.1 is 73.6802. 73.6802. All right, so that was step 4. Now you can see that this is a pretty close approximation. And it's a pretty close approximation because 1.1 is very close to the center. The closer you are to the center, the better your approximation. 1.1 is very close to the center, which was 1. And so with a P3, we should get a pretty close approximation. The last thing we want to do is to determine the error. Okay, and so the error, which is also referred to as the remainder, has the formula, the absolute value of r sub 3 of x. It's going to be less than or equal to f of n plus 1 of a over n plus 1 factorial times x minus c to the n plus 1. Now that looks like a difficult thing to try to remember. But remember, all of this is, and we then is the fourth term in our polynomial, our fourth derivative. This simply means the fourth derivative of f evaluated at a, which we already did, right? So let's figure out what this is. What is this? Well, this is the fourth derivative evaluated at a, and we already found that out to be 81e to the fourth. And then we want x minus c, which is x minus 1 to the n plus 1, which is to the fourth. And then over n plus 1 factorial, which is simply 4 factorial. So there we have it. So the absolute value of r sub 3 of x is going to be less than or equal to this. And then all we want to do then is put in 1.1 is going to be less than or equal to 81e to the fourth times 1.1 minus 1 to the fourth all over 4 factorial. And let's do that in Desmos as well. And going back to Desmos, I put that in down here. We have 81e to the fourth, x minus 1 to the fourth over 4 factorial. Then I evaluated that at 1.1. And the error or the remainder is 0.0184. 0.0184. So it's going to be less than 0.0184. Now, another way of looking at that is that the remainder is the difference between the function value and the polynomial value. So the error is the difference between the function value and the polynomial value. So if we go back to Desmos, here we have the function value, 73.6997. Here we have the polynomial value, 0.6802, and here we have the remainder. If you add this remainder to the polynomial value, you're going to be very, very close to the function value. In fact, the remainder says that the actual remainder will be less than or equal to this amount, right? And so you'll see that that is actually true. All right, so those are the 5 tasks for working with Taylor polynomials and Taylor series. And once we have this down, we're going to be doing a little bit more calculus with these functions and series.